Hello everyone, I hope you're doing well. So in this video, we're going to discuss the solutions for this particular Codeforces round, which was held today, Dytechlab Cup 2022. So we will be discussing the first three questions. Now let us quickly start with the first question. So this particular question says that we have been given some N books and we have been given some K compartments, and we have to divide those N books into those K compartments such that each of them has exactly n by k books. So n would be divisible by k. This is already given in the question, right? So all the character for that particular compartment will be equal to the MEX of all the books in that compartment. So each of the books would be assigned a letter from A to Y, and for that particular compartment we have to add a letter to the result, which will be the MEX of all the characters in that particular compartment. Now we have to form the greatest string that we can form. So for example, let me take the first test case. We have been given CAB, CC, ADA. Let me write it first, or let me just, we will take the first test case, right? So this is the first test case. It says that this is the string and the value of n in k is 12. So this is n and this is k. So each of the compartments will have exactly 4 books, or for the characters, which whatever you say, right? There will be 4 books, right? So what we can do is, to form the greatest string, we can put in the first compartment A, B, C, D, right? So this is possible. The next compartment can have A, B and C again, and the third compartment will be have, so we are just consuming these from here. So we have used this A, we have used another A, we have used a single B, and we have used another B. C we have used 3 times, 1, 2 and 3, and we have used D 1 time, right? So the only characters that we are left are A and C. 2 times A and 2 times 3 times A and 1 times C, right? So this is the only character that we are left with. So the MEX for this particular stack would be E, the MEX for this particular stack would be D, the MEX for this particular stack would be B. So EDB would be our answer in this case. This is how they say that EDB is the answer in this particular case, right? So this was the explanation of the question, right? This is what exactly the question is asking us to do. Now how do we do this? So for every of those stacks, or for every of those compartment, we can just individually find what is the maximum character that we can store here, right? And we can just brute force it through all the ways. For the first compartment, what we can do is, since we have to find the greatest string, right, or the greatest this particular result, then we can start from the first compartment and check whether we can form A here, and then we can check whether we can form B here, then we can check whether we can form C here. So the maximum character that we can form from using exactly 4 books in this case, and in any other general case, we can use at max n by k books, right? So using at maximum n by k books, what is the maximum character that we can achieve? We will find that, and we can append it to the result, right? So let me just show you the code, because we can do it with brute force directly, right? So what I've done is, I've taken 2 integers n and k, and I've taken a string s, and I take all the inputs n, k and s, right? Now I'm storing all the characters, the frequency of all the characters in a map. So that is what I'm doing. I've created a map, and I'm traversing in the string, and for all the characters I'm storing them in the map. Now I initialize my result with an empty string, right? I just run a loop through all the compartments from 0 to k, right? So I'm initializing the add with a, because this is the minimum possible that I can add. So add will be the character that I will be adding to the result. Now I'm initializing count with 0, right? So what I'm doing is, I'm just looping through while count is less than n by k, because at max we can add n by k books to a single compartment, right? So if this particular character is present in the map and its frequency is greater than 0, I just increment add, so that now I have to look for the next character. Otherwise I can just break from the loop. And if in either of the case, I just increment the count so as to indicate that I have included count number of books in my current compartment, right? So whenever I find my character that this is the character I want to add, So for all the values less than that particular character, from A to less than that particular character, I can decrement it from the map and I can like append this particular character to my result. So for each of the compartments, I can individually find or independently find the character, maximum character data I can have for that particular compartment, and I can just add it to the result. And at the end, I'll just print the result, which will be my answer, right? So now let us move on to the second question, which is like we have been given the definition of luxurious number, right? So it says that an integer x is called a luxurious number if it is divisible by root x, right? And we have to take the floor value of root x, right? So there are given some examples of luxurious numbers. For example, the value of root 8 is 2.8484, right? And when we take the C value or floor value, the floor value of this particular thing, then it becomes 2. So 8 is divisible by 2, so 8 will be a luxurious number. So this is the particular question, and the overall statement is we have to find the luxurious number between n and r inclusive, right? We have to find the number of luxurious numbers in the range L and R, and this can be up to 10 raised to the power 18. We have to be careful of, like, we cannot use any loops or any other thing. We just have to find some mathematical derivation for this particular question. So this particular question can be done with a simple observation. If you see, for every number, right, let us just start with some numbers. For example, 2. If I just square it, then I'll get 4, and the next value would be 4 plus 2 6, and the next value would be 8, right? So these are the only values whose square root of 4 would be, the floor value of this particular thing would be equal to 2. The square root of 6, the floor value of this thing will be equal to 2. Square root of 8, the floor value of this thing will be equal to 2, right? As soon as I take the just next number, that is 9, the square root of this value would be equal to 3, right? So for 2, only these are the values whose square root is equals to 2, and these are divisible by 2, right? So let us talk about the next number, 3. So for 3, again there is 9, 12 and 15. So these are the only values that exist, and their square root is equals to 3. The floor value of the square root is equals to 3, and these values are divisible by 3, right? As soon as I just increment 1 in 15, it would be the square of 14, right? So 14, square of 14 is 16, right? 15 plus 1 is 16, and it is the square of number 4. The next number would be 20 and 24. Then for 5, it is 25, and so on, the list continues, right? So you will observe that for every number, if we take any number, the number of its multiples, which are luxurious numbers, for every number x, the number of its multiples which are luxurious number is exactly equal to 3, right? So for there will be exactly 3 numbers which will correspond to the same root, right? There will be exactly 3 numbers, right? So if we have been given a range L and R, right, we can find the square root of this particular number, and we can find the square root of this particular number. So for example, our range is between 6 to 20. Let us take 6 to 20, right? So it will be like this. Right. So this is our range given in the question. So L is 6, R is 20. So for L, we can get the square root as 2, and for R, we can get the square root as 4, right? So it should be 4. If we do square root of 6, we will get 2. If we do square root of 20, we will get 4. So we observe that for every number which is between 2 and 4, that is 3, the list will always be complete, right? For every number present between 2 and 3, the list will always be complete. Or we can also say, if we just include one more list, right? So it can be 24 here. For 25, it will be 25, 30 and 35, right? So for example, if the value of R was, let's say, 30, So now the square root of L, that is 6, would be 2, and the square root of R, that is 30, would be equal to 5. Right. So again, all the numbers which are present between these two numbers are always complete. That means all these numbers are present in our range and they are luxurious numbers. Right. So what we can just do is we can find the square root of both L and R, which is 2 and 5 in this case. For all those numbers, the number of numbers, which is in this case 2, that is 3 and 4 are present, we can just multiply it by 3. So we can get 6 luxurious numbers straight away. Right. So we know there are at least 6 luxurious numbers in our range. Right. What we have done is we have first calculated the square root of L and R, and then all the numbers that are between in this particular range. That means all the numbers that have their luxurious set complete, we can just take it and multiply it by 3. Now for 2 and 5, we can just individually check how many numbers are present in their luxurious set, which are also a multiple of 3 and which also lie in this particular range, a multiple of this particular number. Right. For example, the number 2 can have at max 3 numbers which are luxurious. Similarly, 5 can have at max 3 numbers which are luxurious. Right. So we can just manually check for these 3 numbers how many of them are actually present in our range L to R. So we'll check whether 4 is present. It is not present. So we'll check 6 is present. Yes, it is present. 8 is present. Similarly, for 5, we can check whether 25 is present, then 30 is present, and then 35 is present or not. Right. For each of the numbers which are present, we can just increment our count by 1. Right. So all the numbers that are in or at the border, we can just check manually, and all the numbers which are present between them, we can just directly multiply it by 3. So this is exactly what I have done in the code. As you can see, if I show you the code, so I have taken the range L and R, and I just calculate the square root as LL and RR. So these will be the square root of L and R respectively. So I'm just, if you watch carefully, I'm using square root L and square root L in the second case also, because this is the inbuilt function which calculates the square root more in a more precise way. It is so it will not cause any precision errors because the value of L and R is already very large. So right. So what I'm doing is I'm decrementing R by 1 and I'm RR by 1, which is the square root of the right part, and I'm incrementing LL by 1. So what I'm essentially doing is from here, this particular position, I'm moving to this particular position, and from this particular position, I'm moving here. Right. So I just have to calculate the number of integers present in this range inclusively. Right. So what I'm doing is RR minus 1 minus LL minus 1 plus 1. So this will I'm including both the ranges. That is why I'm doing plus 1. So if count is less than 0, I just do count is equals to 0 because I don't want negative numbers, and I just multiply it by 3. Right, because these are the numbers which will have the complete set of their luxurious numbers. Now I set these two variables left and right as LL into LL and RR into RR. So essentially what I'm doing is I'm just getting to their first element. So for 2, the first luxurious number would be 4, and which is the square of 2, and for 5, the first luxurious number will be 25, which is obviously a square of 5. So I'm just getting to these particular position, and obviously there will be only 3 luxurious number for any integer x. So I am running a loop from 0 to less than 3. Now I check if left is greater than L and left is less than R. This means I'm just checking if that number left is present in the range L and R. I just increment count. Now I just check if left and right are not equal. So there might be a case where the value of LL and RR are actually equal, and the value of left and right will also be equal in this particular case. So I just check if they are not equal and right is present in the range L and R. So right is should be greater than or equal to L, and right should be less than or equal to R. So I just increment count in that case, and now I just increment left by LL by a value of LL so that I can find the next multiple, and I increment the value of right by RR so that I can find the next multiple of it. Right. At the end, I can just print count, which will be my final answer. Right, for all these cases. Right. So this would be the solution for the second question for today's contest. Now moving on to the third question, which is Ela and Crickets. So this particular question says that we have been given 3 pieces of the chessboard. So these are some random pieces and they do not follow any rules of normal chess. Right. So they are initially given in one of these four states, right? It should be an L state, right? So they are always given in one of these four states. Now, what we have to tell, so there was also given an integer n, which states that we have a board of n into n size. Now, these are the numbers that we have: R1, R2, and R3. These are the three pieces that we already have on the board. So we have to tell whether we can reach any of those three. So we have three pieces right here. So we have to tell whether any of those pieces can reach this particular position or not. So in this case, it is 5, 1. In this case, this is 5, 5. Right. So again, this question had a very simple and important observation. We will discuss that observation, right? So let me just create a board first. So for example, this is the board, right? Let me mark my first cricket as here, 1, 2, and 3, right? So these are the initial positions, and obviously these would be already visited, right? So this is already visited. Now, how do these crickets move? So they are actually, these pieces are all actually called crickets. So these can move in the following manner. I'll show you from the example. So like one of them should always cross another of them. They can move in any direction, up, down, left, right, diagonally, anywhere. But the condition is one of them should over cross another like the other one. Like for example, in this particular case, this particular cricket travels above this and get to this position. So it is crossing one of them. Again, this particular cricket like crosses this one and gets to this position like here, right? So like the only constraint on the movement is one of the crickets should cross another one, right? It should like go over another one, right? So we just have to take care of this particular thing. So now we can just track the movements. Let us just try some random movements. If I move 1 to this particular position, it is always possible because it can travel over 2 and get to this particular position, right? So this is, I'll be marking all the positions that are visited with a slight green color. So this is possible, right? Now this 3 can move to this particular position by crossing 1. So 3 can go here and this is visited. This was visited and this is also visited. Now come 2 can come downwards. So it like while going over 1. So this is visited. So this is visited, this is visited, this is visited, and this is also visited. Right. Now what I can do is I can just move 3 from here to here. We are just trying out some random like moves that are possible, right? So this is possible, right? 3 can go from here to here. But if I do not wish to move 3 here, what I can do is this is also visited. We can go here. What I can do is I can just move 1 from here to here. So this can also be visited, right? If I don't want this, what I can do is I can just move 2 from here to here. So this can also be visited. This is also visited, right? And again, if we go to the initial position, now again, if 2 is moved from here, if it is looking something like this, right? Again, I can move 3 from here to here. Then it would be something like this, right? So this whole is visited. This whole column is visited. This whole row is visited, right? If we just imagine the first scenario that 1 was here, 2 was here, 3 was here, then 3 can move here. So this would be visited. 3 can move here. This would be visited. Again, 2 can move here. So this would be visited. Again, 3 can go from here to here. So this would be visited. So there will be a pattern that will form after some time. Let me just show you for this one also. Or we can also actually visit this particular row, this particular column. Let me show you an example. If it was 1, 2, 3 like this. So let me just clear all the other places. So we have proved this can be visited, we have proved this hole can be visited, we have just proved this hole can be visited. Now we just have to check for this particular column for the sake of the example. So one can go here. So this is the current scenario. Then three can go here. So and then two can come here. So one, two, three. This would be the scenario, right? Then one from here can go here. So this would be the scenario, and then two can come here. This would be the scenario. Now let me just mark, right? So this was the current case. Now one can go above two. So this would be the scenario. Again, two can go above one. So this would be the scenario. So essentially, all the cells that are visited at the final stages, these will be all the cells that would be visited. I have marked them with slight green color. These would be all the cells, and this will form a pattern over a bigger test case also. Like if I extend this, if you have observed the pattern till now, the pattern will be every row and every column leaving one space, right? So this hole will be visited, this hole will be visited, then this particular column will be visited, then this particular column will be visited. So it's essentially, if we have started from here, then this column will be visited, this will be visited, this will be visited. If we have started from here, this will be visited. Again, leaving one column, this will be visited, leaving one column, this will be visited, right? So what we are observing, that if this was the pivot point, every row and every column which is at an even distance from it actually is like colored green, or we can visit that particular row or column. So you can just try it out yourself. I reached this conclusion by just manually trying out a few configurations, but there's one like restriction to this particular idea, and we'll discuss this case. We'll discuss that case, right? So if this is the thing, and the pivot is this point, let me just tell you once at which point I'm calling the pivot. So we discussed that this point was the pivot in the earlier and in the previous example, and every row and column which was at an even distance from this pivot was visited, right? So the pivot is, it will always be an L shape, right? So the pivot will be the point where both of the rows and column intersect of the L, right? So if this is an L shape, this would be the pivot, and all the rows and columns which are at an even distance from this particular pivot will be visited, right? But what if the pivot is in one of the corners, right? It can be here, it can be here, here, and here. So these are the only four cases that will not have an optimal answer, right? In this particular case, you have nowhere to escape, right? You cannot go anywhere. Either you can choose this particular element and go here, and then you will choose this and then you go here. So you can travel in this fashion, or you can choose this and go here, and then you can choose this and go here. You can travel in this particular fashion. So if the pivot is in one of the four corners, then this is the only way that you can move, right? Because if you want to move this particular element, it can only go here or here, and both are out of the board, so you cannot go. If you want to move the other element, that is this particular element, then you can go either here or here, and both are out of the board, so you cannot make this move. So if the pivot is in one of the four corners, then these are the only possible moves that you can make. That is, either you can move in the same row as of the pivot, or you can move in the same column as of the pivot, right? So this will be the solution for the third question, that we have to maintain an even distance or the column number, that is 0, 1, 2, 3. So you see, if the parity of that particular column is 1 here, then the columns which have the same parity will be visited, right? So either you can say it anyway, or you can code it in any way. Either the distance should be even or the parity should be same, right? All of those will be visited. And if the pivot belongs to one of the four endpoints or one of the four corners, then the row or the column should be exactly same as of the pivot, only then it will be visible. So let me just show you the code directly now. So I've taken an integer n and I've taken a map of rows and columns. So this will denote like the number of rows, the number of points at that particular row, and the number of columns at that particular point. So I'm just taking three inputs A and B, and I'm incrementing the number of rows at particular point A. I'm incrementing it the count by 1. At particular point B, I'm incrementing the column count by 1, and then I take the input x and y. Now I initialize two variables px and py, which is the pivot point, right? So what I do, if I dot second is equals to 2, that is the frequency of that particular point is equals to 2, I set the pivot, the value of pivot x, which is the x coordinate of the pivot, as I dot first. Why am I doing this? Because as I have already told you that this particular corner of the L shape would be called the pivot, right? And obviously this particular x and y will have frequency 1 comma 1. On this particular x and y will have frequency 1 comma 1. Only the pivot will have the frequency 2 comma 2, right? So this way I can easily find the pivot. I can just check if the frequency is 2, then this is the x coordinate of the pivot. I can traverse in columns. If the frequency is 2, then this particular point is the y coordinate of the pivot. So I just when I have the pivot, I just create a set of pairs. So these are the invalid pairs, that is all the four corners. I just insert all of these four corners 1 comma 1, 1 comma n comma 1, and n comma n into the set, right? Now I just check if the pivot is in one of the four corners. I just do invalid.count. This will return 1 if this particular pair is present in the set. So I'm just checking if the pivot is present in the set. Now what I do is, if it is present, then what I have to do is the pivot, either the x coordinate should be equal to the x coordinate of the pivot, or the y coordinate should be equal to the y coordinate of the pivot. Only then the answer would be yes, otherwise the answer would be no. Now if none of these if the pivot does not belong to one of the four corners, I can just check if the x coordinate has the same parity as the pivot, or the y coordinate has the same parity as the pivot, right? If one of these conditions is true, I have added or in between. If one of these condition is true, then the answer would be yes, otherwise the answer would be no. So this was the solution for the third question for today's contest. I hope you guys were able to understand the solutions. So till the next video drops, keep coding, stay safe, bye bye.